This is section 9.6, which involves the ratio and root tests. I think you will find this section to be a little more refreshing than the last section, so hopefully you like this a bit. It's a little more straightforward than the previous section, but basically we start off with a test for absolute convergence, and that test is called the ratio test. And basically, one of three things can happen. The series either converges absolutely. If this happens, the series will diverge when one of these things happen, or the test is inconclusive when this limit is equal to 1. Now, if that happens, if this limit is equal to 1, then what we'll do is we will apply a different test. Okay, so we need two things when dealing with the ratio test. We need to know what the nth term is, and we also need to know what the nth plus 1 term is. Then we'll divide and find the absolute value and see what happens. Okay, so let's look at our first example. It says use the ratio test to determine the convergence or divergence of the series. If the ratio test is inconclusive, determine the convergence or divergence using a different method. Okay, so let's take a look. As mentioned in the previous slide, we need to know a sub n. That's the nth term, that's just this. So 2 to the n over the quantity n plus 2 factorial. So if that is a sub n, then the nth plus 1 term, I'm going to plug in n plus 1 here and n plus 1 here. And when I do that, I get the following. So n plus 1 plus 2 is n plus 3 factorial. Okay, so once we have these two things, what I want to do is I want to take the absolute value of this. So I'm going to find the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. Well, this is equal to the following. Now, I'm going to have this here divided by this, okay? So this, the nth plus 1 term, divided by the nth term. Okay? Well, remember with division of fractions, we can rewrite this as by using the copy dot flip trick. I don't know if you're familiar with that, but what that means is when we're dividing fractions, we can copy the first one, change the division to a dot, so copy dot, flip the second one. Okay, so we have this absolute value. Now this is where things get a little interesting because we need to apply some algebra rules in order to simplify this. Okay, so this is going to be the most complicated part, so just hang tight, all right? Now, what I can do when I am multiplying these, I can cross simplify. Not cross multiply, but cross simplify. So I can look at these and see if anything can cancel out here. Likewise, I can look at the other diagonal and see if anything cancels out there. So let's see what happens. 2 to the n plus 1 is the exact same thing as saying 2 to the n times 2 to the first. Right? Because same bases, we add the exponents. Well, if that's the case, if this is over this, I can cancel out the 2 to the n's. So I'm simply left with 2. Now let's do the same type of thing here. Okay, now remember that this n plus 3 factorial can be written as n plus 3, then subtract 1, so n plus 2 factorial. Well, if I'm cross-simplifying, the n plus 2 factorials cancel, and I'm left with n plus 3. So this is equal to the limit as n approaches infinity of 2 over n plus 3. Well, n is 0, so if I plug in 0 here or anything bigger, this is going to be positive, so I don't need the absolute value. If I apply my limit here, the denominator increases faster, so this limit is equal to 0. According to the chart for the ratio test, if this limit is less than 1, which it is, then we can conclude that our given converges absolutely by the ratio test. And the ratio test is the theorem 9.17. Okay, so not terrible, right? Let's look at another example. All right, same rules apply. This here is an alternating series. Great. Okay, so if this is an alternating series, that's fine. We don't really need to deal with this right now. So I'm going to say that the nth term is 3/2 to the nth power over n squared. If that's the nth term, then the nth plus 1 term is found by plugging in n plus 1. Okay, so now applying the ratio test, we have the limit as n approaches infinity of the nth plus 1 term over the nth term, which is equal to the following. Now I'm gonna go ahead and apply the copy dot flip trick right away. So I'm gonna have n plus 1, so this, times the reciprocal of this. Okay, because if I have this divided by this, then it's the same as multiplying by the reciprocal. Okay. All right, so this times the reciprocal of the nth term. All right, so we're going to have some algebra involved here, just like we did previously. Okay, so that's the hard part. All right, so this here, we want to try to cancel this out. So we want to somehow write this as 3/2 to the nth power. Well, this is the same thing as saying 3/2 n times 3/2 to the first. Okay, well, if that's the case, then 3/2 n cancels out and I'm left with 3/2. Same type of thing here. Well, in this case, there's nothing I can do to cancel these out. So I'm going to leave this as is. So this is equal to the limit as n approaches infinity of 3/2 n squared over n plus 1 quantity squared. Okay, I eliminated the absolute value because both of these terms are squared and anything squared is positive, so I don't need the absolute value. Now looking at this, I notice that both of these are squared, and I can do a little bit of simplifying here. If I FOIL this out, this is n plus 1 times n plus 1, which is n squared plus 2n plus 2. Okay. And I can make this fraction, I don't want a fraction within a fraction, so I can clean this all up a little bit. So I can write this as 3/2 this way, n squared over what I just FOILed out, n squared plus 2n plus 2. And then I can notice that we have the same degree. So this limit is equal to the ratio of coefficients, which is 3/2. Okay, so looking at the ratio test, that theorem, if this absolute value is equal to something greater than 1, then by the second part of the ratio test, we can say that our series diverges by the ratio test. Okay, not so bad. So that is the ratio test. Well, of course, we have another test called the root test. So this test is nice when we are taking the square root of something. Okay, so again, similar to the ratio test, the root test has 3 parts also. The series will converge absolutely when this occurs. It will diverge when this occurs, and then the test will be inconclusive when this is equal to 1. So just use another test if this happens. Okay. Anytime you have a p-series, it's always going to be inclusive, so FYI. All right, so let's take a look at a couple examples. Okay, we want to use the ratio test to determine the convergence or divergence of the series. So according to the root test, we need to find the following. The nth root of the absolute value of the nth term. Well, in our case, this is the nth term. So all we're going to do is we're going to take this and plug it in right here. So let's do that. So the limit as n approaches infinity of the nth root of the absolute value of this. Now you've probably noticed that there's a lot of algebra involved here. Okay, so yeah, there is. And it's just something you'll have to accept. So a couple things. If I have this absolute value, the absolute value can actually go away really, because what it's saying is you're going to have some odd exponent. And if you have an odd exponent, this is going to be a negative value. Well, the absolute value is going to make this negative go away. This nth root is going to cancel out with this n. So this limit becomes (3n over 2n plus 1 cubed). So all of this simplifies to this. Well, applying the rational roots type thing here that we've talked about 1,000 times, this limit is equal to 3/2 cubed, which gives us 27/8. This is greater than 1, So by the root test, the series diverges because this falls into the second category of the root test. Okay, let's look at another example. All right, so this one is e to the negative 3n. This is n. So plugging this in, we have the limit as n approaches infinity of the nth root of the absolute value of this. Okay, well, this can be rewritten as the following. Okay, well, when I rewrite this, I can kind of see what's happening here. When I rewrite this, I can first of all eliminate the absolute values because whatever I plug in for n, this is always going to be positive. Okay, so I can eliminate the absolute values. Now, remember, anytime you have a radical, you can take the radical of the top and the radical of the bottom. Okay, well, the square root or the nth root of 1 is just 1. So this limit, if I take the nth root of 1, I get 1 over the nth root of e to the 3n. In this case, the n's can cancel out, so the nth root goes away, and this is equal to the limit as n approaches infinity of 1 over e cubed. This is just a constant, so the limit of a constant is a constant. So this limit is 1 over e cubed. This value is less than 1. Since this is less than 1, we can conclude the following, that our series converges absolutely by the root test. Okay, so nothing too crazy. Okay, now another thing about this section is it's all kind of coming together. So you've seen lots of different tests for determining convergence and divergence of these infinite series. So what it's going to come down to is you're just going to be given a ton of different series, and you're going to have to come up with what test you use and when. And that gets a little overwhelming, and I understand that. So here are a couple guidelines that you can follow. So if the nth term approaches 0, you want to see if the nth term approaches 0. Okay, so that's the limit at infinity. If it doesn't, the series diverges. Is it a special type of series? For example, a geometric, piece series, telescoping, alternating. If it is, you should be able to identify which type it falls into and then use the appropriate test. You want to see if the integral test, the root test, or the ratio test can be applied. If they can be applied, great, use it. Different things like that. Now, I've provided for you a summary for all the tests. It's on this slide and the next slide. This can be found in OneNote under handouts. So I would recommend printing it out or having it available so that you can see all these different strategies. Okay, this will become very, very, very helpful for you, especially on a test or quiz if you catch my drift. All right, so this wraps up section 9.6. I hope you enjoyed every second of it.